Hi everyone, and welcome to Dr. G's excursions into the world of mathematics and physical science. And today we're going to look at the all-important concept of the SI unit. Okay, and it's actually an international system of units where we agree on units of length, units of mass, and of course, units of time. Can you imagine what the world would be like if 1 second in Durban was something different to 1 second in London, for instance, or a second in the Amazon jungle? So we know that time, follows a physical process. It's also a biological process. But how does one agree on what is 1 second? And I think that's very, very important in terms of engineering, in physics, in understanding physical processes, in understanding biological process. We've got to stand or come to an agreement, or what I would like to call common ground when it comes to the use of units. So, we are familiar with various units, and we also have an old system of units, and you may have come across the concept of feet or foot. So how long is 1 foot? And as I mentioned, mass, we've also seen people talk about pounds and ounces and also stone. What does that mean? And then, well, obviously we are familiar with the kg, but are we really familiar with the kg? For example, what is the mass or the average mass of an apple? To me, I think it's about 156 grams. How would I know that? Well, every time I get into a little grocery store and I see a scale there, I take an apple, place it on the scale just to get a measure, just to get a feel for different types of objects. So an average mass of an apple is about 150, 156 grams. Time, time waits for no man. It just like sands through the hourglass. And we have various ways of keeping time. But what does it really mean? So hopefully we bring the whole idea of units into perspective today, and that when you're out there, you are ready to actually understand the universe based mainly on what we have put together as units of length, mass, and time. Fundamental SI unit, which I like to use to bring to your attention, is the length. And very quickly, the SI unit for length is the meter. The meter. It's very, very important. Not the kilometer, but the meter. And it turns out, and we all know this, hopefully, that 1 kilometer is 1,000 meters. A meter can be broken up into smaller units called centimeters. So 1 meter is 100 centimeters. And you will be surprised how many people actually think that 1 meter is 1,000 centimeters. No, it's 100 centimeters. And if you break that even further, then we know that 1 centimeter is about 10 millimeters. Not about, it is exactly 10 millimeters. All right, so if you look at your fingernails, that'll give you an idea. So your thumbnail would give you an idea of about 1 centimeter. And it's also very, very important to get a feel for magnitude or size of these things. You need to relate them to everyday life. For instance, the length of a ruler, we all know, is 30 centimeters. So how long is a kilometer? You try to imagine this in terms of real physical situations. We all know the 100-meter sprint during the Olympics. We're familiar with that sort of distance. But have you actually run 100 meters? I mean, what is your record of a 100-meter sprint? Yeah. SI units further in terms of length, all the units that are still in use, and this can cause lots and lots of confusion. For instance, the mile. The mile is 1,760 yards. Oh my goodness, now what is a yard? Well, 1 mile is also 5,280 feet. Aha, closer to home. And then 1 yard is 3 feet. Whew, gosh, 1 foot is 12 inches. This is a lot. Now, I just want to bring it back to what we know, and let's very quickly have a look. And what I like to see down here, for instance, it tells me that 0.31 meters is 1 foot. And further down, I think we can all basically see this, that 1 foot is about the length of a ruler. It's about 30.48 centimeters. So I like to think of a foot about a ruler length. So it's all making sense to me now. But, we also speak of inches, and I think that's very, very important. So let's just try to break that down. That wasn't in the table. So 1 inch is about 2.5 centimeters, 2.54 centimeters. Okay, so people speak of 6-inch nails, for instance. So 1 inch is about 2.54 centimeters. And now you can bring this back into the old units. So I tend to remember a foot is about 30 centimeters. And then 1 inch is about 2.5 centimeters. And so then I can start deriving all the other older units in terms of the SI units that we're so familiar with. It's really difficult to remember this, but there's so many apps out there now. You can just scan using your phone, you can Google, and pop, things come along. But every now and then I think it's also useful just to use the old computer called the brain to do these conversions and keep yourself healthy. Okay. Derived units, we speak of length of a ruler. We speak of, say, the length of a track. But then what about area, for instance? We take a triangle, let's take a rectangle. Let's go very simple. So a rectangle over there. The height of the rectangle is 1 meter. And let's just say the base here is about 2 meters. No prizes for guessing that the area of this rectangle is length times the breadth. So it's 2 times 1. And what is the units for the rectangle? Well, it's very easy to see that. It's 2 meters by 1 meter. So that becomes 2 meter squared. Now, it's interesting because if the lengths were given, say, in terms of centimeters, so take a little rectangle over there, 2 centimeters, the length is 1 centimeter. Now, what I want is the area of this rectangle, not in centimeters squared, but in meters squared. Interesting. So the area of this little rectangle is length 2 centimeters, and then we're going to go 1 centimeter, and the area of this little rectangle is going to be 2 centimeters squared. Tiny. What will this be in meters squared? Do I divide this by 100? Do I multiply by 100? 1,000, 10,000, 1 million? Oh my goodness. So what I like to do here is say, well, it's in centimeters. So let's just convert each of the sides straight away from centimeters to meters. So how do I go from centimeters to meters? You will recall that 1 meter is 100 centimeters. So then 1 centimeter, let's go here, 1 meter is 100 centimeters. So what is 1 centimeter? It's 1 over 100 meters. 1/100th of a meter would give you a centimeter. Does that make sense? So 2 centimeters would be 2 over 100 meters. And this 1 centimeter that we have here will be 1 over 100 meters. So that's 2 times 1 is 2, and 100 times 100 is 10,000. Meter times meter is meter squared. A nice proper way of writing this would be this 10,000 there. So it's 2 times 10. Because you're dividing by 10,000 would be minus 4 meters squared. But we'll come back to the whole idea of exponents and significant figures in our lesson that's coming up shortly. So this tiny rectangle has an area of 2 times 10 to the minus 4, or 2 over 10,000 meters squared. All right. And similarly, when we speak of, a volume, we know that 1 liter, we're familiar with the liter, but are you familiar with decimeter cubed? So 1 liter is actually 1 decimeter cubed. Decimeter. That's 1/10 of a meter. Is that not right? 1/10 of a meter. So how do we get decimeter? Well, that's 1 decimeter times 1 decimeter times 1 decimeter. But 1 decimeter is 1/10 of a meter. So it'll be 1/10 of a meter times 1/10 of a meter times 1/10 of a meter. What is 1 over 10 times 1 over 10 times 1 over 10? No prizes for guessing over here. It's 1 over 1,000 cubic meters. And suddenly we are now in SI units. Remember, the SI unit for volume is the cubic meter. And nice way of writing this is 1 times 10 to the minus 3, because we're dividing by 1,000 cubic meters. So now I've asked you or shown you how to convert a liter into cubic meters. So the next time you go to the little shop and you want to get a liter of milk, you can always ask for 1 times 10 to the minus 3 cubic meters of milk and wait for the response. Anyway, that's so cool. So you need to start playing around with these things and appreciating how you'd convert, say, from just a simple SI units. A very important unit, a fundamental unit is a concept is the mass, and the SI unit for mass is the kilogram, which is very, very interesting. Yeah. So if you think of length, we said the SI unit is the meter. For mass, it's the kilogram or kg. And kilo, so 1 kilogram is 1,000 grams. And 1 gram, tiny bit, is now 1,000 milligrams. So we can break this up into smaller and smaller and smaller units. So if you put those two together, if 1 kilogram is 1,000 grams and 1 gram is 1,000 milligrams, can you tell me what 1 kilogram is in terms of milligrams? Would that not be 1,000 times 1,000, which is 1 million milligram? Does that make sense? Correct. Now let's go the other way, from small to big. So we can say that implies that 1 milligram is now 10 to the minus 6, 1 millionth of a kilogram. Interesting. But when we speak of atoms, when we speak of molecules, that's far less. I mean, those numbers are so tiny that we cannot even speak of milligrams. You've got to speak of micrograms and atomic units. And that's where the idea of units, SI units, conversions, all of them become fundamentally important. Non-SI units mass. Man, this is big business. Weight loss, mass loss, man. Switch on the TV, Google, YouTube, it's all over the place. Everybody's wanting to do something with mass, either gain it or lose it. So we know the SI unit is the kilogram, and then suddenly we got this concept of pounds, So it's about 2.2 pounds. It's really difficult to wrap your minds. You watch programs like The Biggest Loser, and suddenly the guy has lost 100 pounds. 100 pounds, man. And you're thinking, well, if I lost 100 pounds, I would disappear. But what is 100 pounds? If 1 kilogram is 2.2 pounds, lbs. So if you lost 100 pounds, how many kilograms is that? Bring out your calculators. Come on, I'm not talking about those little push button things. I'm talking about the old calculator called the brain. And to complicate things even further, we speak of stone. 1 stone is 14 pounds. And eventually 1 kg is about 0.157 stones. It's very difficult to remember these numbers. 0.15 stone, 1 kg. I'd rather stick to SI units, except, we're out there in the real world. We are going to come across the concept of pound and stone. And if you Google pounds, it says it's a unit. This is very interesting. It's a unit of mass/weight. Oh my goodness. So is pound a force? Pounding? Or is it mass, quantity of matter? Okay, very interesting indeed. Weight versus mass, Mass is the stuff that you made up of, so that cannot change. If your mass is 50 kgs on Earth, I take you to the moon, your mass is still going to be 50 kgs. But your weight is interesting, because the weight depends on your mass, correct? But it also depends on this little g, and that's called the acceleration due to gravity. We all will remember this, acceleration due to gravity. Now, if you're close to the surface of the Earth, like on the Earth's surface, depending where though, we can approximate g to be about 9.81 meters per second squared. What does this mean? It means that if I dropped an object in the absence of air resistance, its acceleration towards the Earth's surface, towards the Earth's center, is going to be close to about 10 meters per second squared. So a 50 kg person, mass 50 kgs, their weight would be roughly 50 times, let's go 10, which is about 500 newtons. That's the force of attraction between yourself and the Earth. It's about 500 newtons. Now, when I take you to the moon, and some people believe we haven't been to the moon and we still live under a dome, the acceleration due to gravity on the moon is 1/6 that of Earth. So your weight on the moon will be, in this case, if you are 50 kgs, would roughly be 50 times 10 over 6, or 500 divided by 6. That would be your weight on the moon. If you go into Jupiter, would your weight be larger or smaller? It's going to be much larger, because the acceleration due to gravity is so much larger on Jupiter than on Earth. But your mass will still be 50 kgs. All right. Time. Wow, this is an interesting concept, Our lives are ruled and governed by time. From the moment we get up in the morning by that alarm clock, and then we get into, I would like to call, little episodes, when the siren goes, school to start, work to start. Time really governs us. And in a way, it's not so much the biological clock, but it's the external time put out by systems, So it's very interesting. The second has been defined as exactly times the period of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. What did I just say over there? But scientists, yes, we define 1 second as being just what I said, and it's very interesting if you study atomic physics. All right. Now, define the second as the SI unit, and I think this is very important. So the second is the SI unit for time. Then it's important that we be able to convert, say, an hour to seconds. So 1 hour, we know, is 60 minutes, but every minute has 60 seconds. So if 1 hour is 60 minutes and 1 minute is 60 seconds, surely there must be 1 hour is 3,600 seconds. Do you agree? The other very, very important timescales in physics, especially the little ones, is the millisecond, which is 1,000 of a second. Microseconds are very important. Fast process, especially on the atomic scale, they measured in terms of microseconds, and then also nanoseconds. So microseconds is like 1 millionth, and 1 nanosecond is 1 billionth of a second. Of course, There are smaller and smaller timescales in the universe. There are also larger timescales in the universe. Because, for instance, you ask yourself, how old is the Earth? Well, it's roughly about 4.1 to 4.3 billion years. How old is the universe? The universe, well, it's relative depending on who you ask and on what particular day. Cosmologists are always wrong, but never in doubt. And they would tell you it's about 14.6, give or take a couple of giga years, so about 14.5 billion years for the average age of the universe. But time is important, you know. We think of time as being a constant flow, just like a river, you know, it's constant flow. But as you get into higher physics, you realize that time is not constant. It's relative, that people measure different times depending on the relative motion between frames. So if you're really interested in that, you want to check out Einstein's theory of special relativity. Very interesting concepts there. Okay. Yeah, I'd like to bring that to an end, but have fun trying to convert and trying to understand, especially the old units and obviously the more recent units as well. So thank you very much, and we will see you soon.